Hello, and welcome back to CS300 Introduction to Algorithms. Last time we talked about the virtues of computer science, the 4 or 5 paradigms that arguably distinguish computer science and science in general from electrical engineering and engineering in general. And today we're going to briefly recall those, and then we're going to apply them. Let me show you the slides. So the paradigms include emphasis on the power of abstraction, where we deliberately ignore low layers such as hardware details, transistors, quantum mechanics, or bit level, and instead focus on high level to get a high level perspective on the problem under consideration. And problem specification is important of the virtues of computer science. Only after problem has been specified, we can start designing algorithms as opposed to start writing code and analyze these algorithms, their correctness and their cost, with emphasis on asymptotic cost as opposed to empirical and absolute running time, because asymptotic cost is a universal property of the algorithm, independent of, and that can later be tailored to the specific situation, the specific computer hardware, and the specific input, whereas asymptotic refers to inputs, infinite sequence of inputs of growing size. And so this is a universal measure, and it depends on semantics, namely the question of which operations did we use in the design of the algorithm, and what is the cost of each such operation? Do we simply count the number of operations when analyzing an algorithm, or are we interested in a more closer but also more involved and perhaps more realistic assessment of the algorithm's performance, where each operations is charged with cost depending, for example, on the data that it operates on. And final, proof of optimality of the algorithm. Once we have succeeded in proving an algorithm optimal, then our job is basically done. Then we can hand over that algorithm maybe to electrical engineers in order to implement that and to start optimizing that algorithm according to the Donald Knuth saying that premature optimization is the root of all evil. But after we have, as computer science, identified the asymptotically optimal algorithm, then is the right time to start optimizing the constant factors that we have been ignoring so far. And as an example, I'm going to briefly recall in the next slide our abstract powering problem as example of a specification, the algorithms that we've devised for that problem and analyzed. And the last one, which we were able to prove optimal, this algorithm is called square and multiply. So that's a name you might want to keep in mind, because we're going to actually apply that algorithm and adopt that from the abstract setting to the specific setting of computing Fibonacci numbers, where the objects that we're going to multiply are not abstract entities anymore, but actually matrices of variable size and of various entries, namely integers of variable length. So that's all planned for today, and we're going to we're going to devise 4, maybe arguably 5 algorithms, different algorithms for computing Fibonacci numbers, algorithms of increasing efficiency in the asymptotic sense, algorithms that also use increasingly powerful primitive operations. So there's kind of a trade-off that we're going to see. More powerful operations means intuitively means maybe we will need less and less of these, but in turn more powerful operations. But at the end of the day, all operations need to be boiled down into processing bits, because that's the only thing that our digital computer can do. So for realistic estimate of our algorithms, we will first look on the high level of the abstraction hierarchy, and then look more closely on the bit level to get a better prediction of the performance. And we're going to see 4 algorithms of increasing efficiency in this level, and the 5th algorithm, but that's a kind of a spoiler for now. And maybe we're going to close with a master theorem about recurrences and their applications in the analysis of recursive algorithms, because that's what we're going to do at the end of this chapter 1. We're going to look at various algorithms for polynomial multiplication, again pursuing this meta loop of algorithm design, analysis, proof of optimality. If it fails, start over again, design a better algorithm, analyze a better algorithm, prove that optimal. If still not optimal, continue again and again. And we're going to do that actually infinitely often for polynomial multiplication. And we close with an open problem of asymptotic cost of matrix multiplication. So that's our plan for today. And as promised, let's start with a recap of the abstract powering problem and the algorithm we've devised. For the abstract powering problem, we consider some monoid. A monoid is a very general mathematical structure, abstract. The only condition is that it supports multiplication of its elements, and that this multiplication must be associative. It need not even be commutative. So it covers many examples. For example, integers can be multiplied, satisfying the associative and the commutative law. But also polynomials can be multiplied, satisfying the associative law, and depending on the coefficients of the polynomials, polynomial multiplication is commutative or not. Matrices can be multiplied, satisfying the associative law, but not the commutative law. So it's really very generous, general mathematical structure. And in accordance with this structure, we consider algorithms that use only that operation, namely only multiplication. And we're going to count the multiplication, ignoring details such as how long does every single operation take. And later, when we apply it, adapt that abstract algorithms and the abstract powering problem to a specific powering problem and specific algorithm, then we're going to look more closely and perform a more refined analysis. So that's our goal for now. And let's recall the recursive algorithm that we devised after our initial trivial algorithm that used the linear number of multiplication, the so-called square and multiply algorithm. And I'm refraining from spelling that out in pseudocode, but instead just present you with a mathematical equation and leave it to you to turn that into a pseudocode. So the first equation is, in case that n is even, then the nth power of x can be expressed as the squared of the n over the second power of x. So that's a implicit recursive algorithm that applies to the powering problem in case with n replaced by n over 2, and then one additional multiplication, namely the one expressing the square operation. That means multiply the result of the recursive call to itself. Do not make 2 recursive calls, that would be redundant, but instead save the result and then multiply it to itself. And that's valid in case if n is even. If n is odd, then n over 2 is not an integer, and thus we cannot, it's not an instance of the powering problem to raise x to the n over second power if n is odd. So in case n is odd, we take an alternative approach, namely raise n to the n minus 1 over 2 power, which in this case is an integer, positive integer, so it's another instance, and it is justified to make a recursive call. And then again, square the result, multiply it to itself, and then perform another multiplication in order for the mathematical equality to really hold. And so these two equations together give rise to recursive algorithm. And we're going to analyze the cost of that algorithm according to our paradigm here, namely counting the number of multiplications used by this algorithm, disregarding the kind of any other aspects that could affect the cost of each multiplication itself. And it's easy to arrive at the following recurrence. So if we are asked to raise it to the first power, then there's nothing to be done. So the cost is 0. Otherwise, make a recursive call. This is covered by this. So T of n denotes the number of multiplication used by this recursive algorithm for raising x to the n power. That's the cost of the recursive call, raising x to the n over the second power. And we combine both cases here by taking this and round it down. So that's the same for both. And either +1 or +2 additional multiplications, depending on whether n is even and odd, or n, again, we're going to combine both into one inequality by taking the larger, the worst case, +2. So that's our recurrence, and this recurrence can be solved easily using mathematics and see that T of n is at most 2 times the binary logarithm of n. So that this is a logarithmic time algorithm, but again, and I must emphasize that with time here, we mean abstract time, namely the number of multiplications used. And we've been able to prove that algorithm optimal asymptotically. And so from that perspective, we can now stop. But a few slides later, we're going to kind of apply and adapt that algorithm to specific monoid. And then we're going to analyze more carefully, not just count the number of multiplications, but also take into account how long each multiplication takes and the dependence of what that depends on. So that was our recap from last time, and now we start with a problem devising, analyzing, and proving or disproving optimality for algorithms computing Fibonacci numbers. You all know Fibonacci numbers, right? And they are commonly introduced with this recursive definition. There are other ways as well, but for now, let's focus on this recursive definition. And you know that F2 is then 2, F3 is 3, F4 is 5, and so on, 8. You know the drill. And one thing I'd like to record for later use is that the value of these Fibonacci numbers grows exponentially in n parameter. And this is easily also proven by mathematical induction. If n minus 1 is at least 2 to the n over 2 minus 1, and if n minus 2 is, then also the sum is at least, yeah, you get the picture. To it yourself, please. And this recursive definition of Fibonacci number immediately gives rise, literally almost, to a recursive algorithm computing Fibonacci number based on the very same equations, namely if n is equal to 0, return 0. If n is equal to 1, return 1. That's the two base cases. And other ways make two recursive calls with parameter n minus 1 and parameter n minus 2, add the result, and that's the return value. So that's our algorithm, and according to the virtue of computer science, we need to verify first, assert correctness, but that's trivial because, right, algorithm immediately is in agreement with the definition of Fibonacci number, provided, here's already an important, interesting subtlety, provided that the integer data type which the algorithm builds on implicitly is the mathematical integer data type, that is, if provided there are no wraparound effects, for example, in the addition. If addition operates on non-mathematical integers, but on hardware integers, and there's a possible wraparound, then this algorithm is not correct. But let's for now suppose these are really mathematical integers, then a correctness is immediate. And so next step is about the algorithmic cost, asymptotic cost of that algorithm. And to this end, I'd like to you to observe that basically the number of operations performed by this algorithm is the same as the value of the Fibonacci number it is calculating. Let me say that again. So if n is equal to 0, then basically performs this operation, and let me be generous and ignore that up to constant factors. That's negligible. If n is equal to 1, then it performs this operation after performing this. So then that's already one operation. And if n is larger than 1, it inductively calculates the n minus first Fibonacci number, which according to hypoduction hypothesis takes that many operations, and calculates the n minus second Fibonacci number, which again by induction hypothesis incurs that many operations, and I'm going to ignore the cost of the addition for now. So the baseline, what I'm trying to say here is that the asymptotic cost of this algorithm is up to some constant factors and shift in the argument, basically the same as the Fibonacci number's value that it is calculating, and in particular, it is exponential as we observed here before. So long story short, this is an exponential time algorithm. Our first algorithm, naive algorithm, immediately derived from the mathematical formula, but highly inefficient exponential time algorithm, which immediately leads to our question following the paradigm and meta-optimization of computer science. How about a more efficient algorithm? Can we devise a more efficient algorithm? One thing to observe here is that this algorithm performs a lot of redundant calculations. So in order to calculate the n Fibonacci number here, the second recursive call it makes for the n minus second Fibonacci number. But this recursive call, in turn, asking for the n minus first Fibonacci number. If we spell out this recursive call, then next thing it does is also calculate the n minus second Fibonacci number. So the n minus second Fibonacci number is actually calculated twice by this recursive algorithm. The n minus third Fibonacci number is calculated even more frequently, and so on. So there's a lot of redundant calculations going on. And this is the core idea to our second, more efficient algorithm. Avoid redundant calculation, only focus on the two Fibonacci numbers that we're actually currently interested in order to calculate the next one, and then discard the previous, so that also saves space. So the first algorithm performs at least fn additions, which is exponential, and this iterative algorithm turns out to get away with a linear number of additions. So let's first look at the algorithm and verify its correctness intuitively. So these are the first cases, right? The first case, and this is the second case when n is equal to 1. And this is the previous Fibonacci number. So this is kind of the current, and this is the previous. This is the n minus first. Now, if n is equal to 0, then or 1, then we're actually done and just return this. Otherwise, we repeatedly climb up kind of from to the next and next higher Fibonacci number. In each iteration, we decrement actually the counter. So the value of n doesn't really matter. What really matters is how many iterations of that loop the algorithm performs. And that's basically roughly n iteration. In each loop of iteration, the loop counter is decremented until it reaches n, and then the algorithm terminates. And in each iteration of the loop, what the algorithm does, it takes the previous, L for last, and the current Fibonacci number and adds them, and stores that in the new current, and the previous current becomes the new last Fibonacci number. So here, make a triple switch. So this is the gist of the algorithm, an iterative algorithm. And I've just argued about its correctness, and now we proceed to look at its cost. We analyze its cost, and that's easy based on our observation that the number of loop iterations is linear in n, so that's a linear time algorithm. Linear in the sense that it uses a linear number of operations on integers, disregarding the length of the integers it operates on. So in order to get so from a high level, that's a linear time algorithm, the number of integer operation, and the low level, counting the number of bit operations, we have to express every single assignment here and addition as a sequence of bit operations. And we know that adding or assigning n-bit integers, each such operation costs n bit operations. So for estimate of this algorithm performance in the bit cost measure, we need to multiply the number of iterations of a loop by n, the binary length of the Fibonacci numbers being calculated, because remember, since the Fibonacci numbers have value, which is exponential, their binary length is linear in n. So each operation is carries kind of a overhead in the bit cost model of O of n, making it a quadratic time bit cost algorithm. So counting only additions and assignments, it's linear time. Counting bit operations, it's a quadratic time algorithm, which is polynomial time algorithms are already a huge improvement over the recursive exponential time algorithm. But now we start to Donald Knuth's paradigm and try to further optimize that in the asymptotic sense, right? So we are focusing here on asymptotics and want to get down from quadratic number of bit cost, bit operations, and to this end, right, so how far down can we go and expect to go? That's maybe a good question to ask. How far down from quadratic bit cost? And the observation is that in the bit cost, the nth Fibonacci number has at least n over 2, so a linear number of bits of output. So that's really something that no algorithm can beat in the bit cost sense. Any algorithm requires at least O of n bits for the output part. So the range where we can hope for some improvement is from n squared of this algorithm bit operations here, and maybe towards linear number of bit operations. And that's what we're going to do now with the third algorithm. And our third algorithm, well, first let me emphasize that these two algorithms both use only integer addition as primitives and assignments, right? So our third algorithm will make use of integer multiplication so that it uses a more powerful paradigm on the high level of abstraction. Later, we're going to analyze that algorithm, third algorithm again, on the low level in terms of the bit cost. So what is the third algorithm? The third algorithm is expresses the Fibonacci numbers recurrence as a matrix recurrence, right? So here you see the nth Fibonacci number and the n minus first Fibonacci number, and rewriting this equation, that's the n minus first and n minus second Fibonacci number added, right? Row times column. And the n minus first Fibonacci number is just the n minus first Fibonacci number, so nothing new happening here. So that's a kind of rewriting. So just mathematics, nothing has happened here. But now we can apply the same again here to this pair of Fibonacci numbers, which means it's again the same matrix. Multiplied now with the vector fn minus 2 and fn minus 3, and so on. So by induction on K, we can easily see that this is the same matrix raised to the kth power, multiplied to the tuple of the n minus kth and n minus k minus first Fibonacci number in a pair. So this is just mathematics, but finally applying that to the case where k is equal to n minus 1, we do arrive at a kind of explicit mathematical expression for the n Fibonacci number, namely when k is equal to n minus 1, This is f1 and this is f0. And this is to be multiplied by this matrix raised to the n minus first power. So this is a almost explicit mathematical expression, almost, because it doesn't say much about what the result of this matrix raised to the n minus first power. On the other hand, this mathematical expression immediately gives rise to algorithm, our third algorithm, namely take the matrix here, raise it to the n minus first power, and multiply it to 1 and 0, and then we're done. Or just take this entry from the resulting matrix. So the baseline here is our third algorithm, basically expresses Fibonacci number calculation in terms of matrix multiplication. And you recall, we had a very efficient, provably optimal algorithm for the abstract powering problem, and now here we have a concrete powering problem. Our previous algorithm for the abstract powering problem had a logarithmic running time. So applying that, adapting that to Fibonacci numbers, it seems like it gives rise to a logarithmic time algorithm. So exponential time, linear time, logarithmic time, but this is only counting the number of operations, right? And remember, in the abstract powering problem, we were counting the number of multiplications of the abstract objects under consideration. And in this concrete situation, the abstract objects are these 2 times 2 matrices of integers, right? 2 times 2 matrix of integers. So in order to get a realistic estimate of the cost of our square and multiply algorithm, we need to take into account not just how many such matrix multiplication it uses, logarithmic number, but also what is the cost of each of this single matrix multiplication. Because at the end, we need to boil this every matrix multiplication down to integer additions and integer multiplications. So how many integer additions and integer multiplication does it take to multiply 2 times 2 matrices? Fortunately, that answer to that question doesn't really matter because it's a constant, right? Whether this constant is 8 or 12 or whatever, whether we count all of them or only some of them, details can be ignored in our asymptotic big O analysis. So the number of integer additions and multiplications used by adapting the square and multiply algorithm is just a constant factor away from log n. That's the first message to take away from here. But we also need to take into account what is the bit cost of each of these integer additions and multiplications when expressing the square and multiply algorithm in terms of operating on these 2 times 2 integer matrices. And here, really the length of the integers under consideration comes into play. So superficially, this seems like constant integers, only 1 and zeros. But after raising this to higher and higher powers, the integer entries in the matrix, still integers, but then they grow in value. And here the observation is that they are always bounded by the value of the nth Fibonacci number. So I leave that to you to verify and prove by induction that raising this matrix to the n minus first power, this we already saw is going to, this position is going to store the n minus first Fibonacci number, and here the previous Fibonacci numbers. So long story short, the entries will grow exponentially, but will remain bounded by the Fibonacci number we're calculating, and thus in particular the binary length will be at most n. Remember, Fibonacci numbers grow exponentially in value, so their binary length is, which is roughly the logarithm, will be linear in n. So that means when expressing that algorithm using the abstract powering problem and square and multiply, then we arrive at algorithm whose bit cost is constant factor for the matrix multiplication times n for the binary length of the Fibonacci number. Now actually n log n, because as you recall, the bit cost of integer multiplication, the optimal, the world record algorithm is n log n bit cost for each integer multiplication, and another log n for the number of multiplications incurred by the square and multiply algorithm, so that this algorithm, the third algorithm in the bit cost model, has bit cost n log squared of n. We say that again. Our third algorithm, the algorithm based on this matrix powering approach, abstract mathematical insight into Fibonacci number, gives rise to our third algorithm, which I didn't spell out. And the third algorithm has a logarithmic number of integer operations involving addition and multiplication, and bit cost is n times log squared of n, where the number of multiplications times the cost of each matrix multiplication is at almost n log n according to the world record algorithm, using the world record algorithm for integer multiplication. So to summarize, here we had an exponential time algorithm. Here we had an algorithm with a little number of integer additions and a quadratic number of bit operations. Here we have an algorithm using a logarithmic number of bit additions and multiplications, which closer analysis is an algorithm using n times log squared n many bit operations. So following our paradigm of first looking at the abstract and then gradually refining to get more involved and also more realistic predictions of the actual performance on the bit cost level. So that's our third algorithm. And now we seem to be close to optimal. Recall, this algorithm has a kind of overhead of logarithmic squared compared to the mere time it takes to output the result, which is a n-bit Fibonacci number. So this algorithm has n times log squared bit cost, and it takes already n of bits to time bit operations to output, so it's the overhead is at most log squared, which is a very slowly growing function. Remember our slide about the absolute running times of different computers, very fast computer, very slow computer, running a logarithmic time algorithm like this one, as opposed to one running an exponential time algorithm like this one. So this is a kind of a good example of the columns in our slide of emphasizing the importance of asymptotic growth. And also observe that here we're using more and more powerful operations, first only integer addition, but in our third algorithm, it's actually quite some hierarchy of algorithms. So on the top level is our abstract powering problem and the abstract square and multiply algorithm. This one is built on top of an algorithm for multiplying integer matrices, which is the kind of objects that that our abstract powering problem is applied to and tailored to. And the integer matrix multiplication in turn algorithm in turn is expressed as a sequence of integer multiplications and integer additions, namely row times column of the integer entries in the matrix, right? Row times column means integer additions and integer multiplications. And the integer additions in turn are expressed as a sequence of bit operations, and the integer multiplication operation in turn are expressed using the world record algorithm that I have not introduced, but only referred to you on the previous part. So there's really a hierarchy of algorithms that are third algorithm builds on top, and on the bottom of everything are bit operations, namely n times log squared. So that's 3 algorithms, but I've promised you 4 algorithms. So let's now look at the 4th algorithm. And the 4th algorithm is based on Binet's formula. Binet's formula is arguably an even more explicit expression of Fibonacci numbers, this time using the golden ratio. The golden ratio, you see defined here, is 1 times the square root of 5 divided by 2. And one thing to observe here is that this is not an integer anymore. So far, everything we've been devising, all algorithms, all data, turned out to be positive integers, but now we leave the realm of integers, and we even leave the realm of rationals, of fractions. This is not a rational number anymore, it's an irrational number. Well, 2000 years ago, a Greek mathematician was drowned by his colleagues for proving that there are irrational numbers, but nowadays I can fortunately say that freely this is an irrational numbers, no repercussions anymore. And this irrational number is the basis of Binet's formula, expressing the nth Fibonacci number explicitly as the nth power of the golden ratio minus 1 over the golden ratio negated and raised to the nth power, and the result divided by 5. And this is an extremely surprising formula if you think about it, because the right-hand side is taking irrational number, raising it to the nth power, subtracting another irrational number raised to the nth power, dividing by square root of 5, whereas the left-hand side is an integer. So there's no reason whatsoever for the right-hand side to be an integer, right? This is extremely unlikely, the right-hand side involving all these irrational numbers, not even rational numbers, to result in an integer. But I encourage you, I urge you to prove by mathematical induction Binet's formula that the right-hand side even is 0 and 1 when n is equal to 0 and 1, and satisfies this recurrence. So extremely surprising. But here in this lecture, I'm going to skip over that part and use that to devise an algorithm. And well, again, there's no need to spell out pseudocode. Basically, take this golden ratio, raise it to the nth power, for example, using the square and multiply algorithm. Take the negative inverse of the golden ratio, also raise that to the nth power, subtract one from the other, and divide by the square root of 5. Now this algorithm, well, I've already emphasized and can only do it again. This algorithm now for the first time does not operate on integers anymore, not on finite bit sequence, but on irrational numbers. So when counting only the number of operation, this looks like a logarithmic time algorithm, one of the fastest asymptotic growth rates of asymptotic growth, but this comes at the cost of using extremely powerful operations, operating on extremely rich data, namely on irrational, not necessarily rational numbers. And in order to get a realistic prediction of the performance of this algorithm in terms of bits, we first need to agree on how to encode irrational numbers as hopefully finite sequences of bits. This question leads far beyond the purpose of this introductory course on algorithms, so I'm not going to discuss that. It's a matter of definition and then analyzing the bit cost of operations in that encoding. That's the topic for another lecture, advanced lecture. So for now, let's just suffice it that this is so far the asymptotically fastest algorithm, but also using the most powerful so far and operations on most expressive data type. There's maybe even a fourth algorithm which I want to close with for now, namely an algorithm that uses even more powerful operations like logarithm, natural logarithm, and exponential function. Exploiting that, we can express this raising phi to the nth power, not just using square and multiply, repeated multiplications, but in this way using only one multiplication, but also using more powerful operations like logarithm and exponentiation. And then Binet's formula gives rise to a constant time algorithm, but constant number of extremely powerful operations. Maybe the logarithm here even exceeds the realm of algebraic numbers and function. It's a transcendental function, and so is exponentiation. So perhaps even more efficient algorithm, but even more powerful and even more unrealistic operation it builds on. So to summarize, we've seen 4, maybe 5 different algorithms for calculating Fibonacci numbers. Some algorithms I've deliberately refrained from spelling out in pseudocode, but their computational cost would accelerate from our first algorithm with exponential to a polynomial to n times log squared n to logarithmic and finally to constant time, but at the expense of using more and more powerful operations on more and more rich data types, and thus becoming maybe more and more unrealistic with their actual performance, or even questionable whether this can be implemented at all. For example, floating point numbers are commonly used in order to express rational or irrational or even transcendental numbers, but only by approximation. And as part of these approximations, they do incur rounding errors. And these rounding errors may and will result in the right-hand side here. For example, when implemented naively in floating point numbers, the right-hand side probably will not be an integer, and even rounding to the closest integer may not yield the correct integer on left-hand side, not to mention here this case. So floating point numbers can be realistically analyzed in terms of the number of operations regardless of the data that they are processing, but the result, the correctness of algorithm based on floating point numbers is not only questionable, but in general simply wrong. So yeah, that concludes our discussion of algorithms for calculating Fibonacci number. We've seen 4, maybe 5 algorithms, each time following our paradigm, our meta loop of algorithms, trying to prove them optimal. And of course, a constant algorithm is always optimal, but also in this setting, at least, it's unrealistic. So that's all for this part about Fibonacci numbers with the various algorithm of increasing efficiency, but also with increasing operations as primitives. So that's what I wanted to emphasize here for now. So, and finally, as a preparation for the next part about polynomial multiplication and algorithms, let me recall the master theorem about recurrences. Recurrences occur frequently in the analysis of recursive algorithms. So this is going to have many applications, but for now, let's state it in a mathematical sense. Let f be a function from natural numbers to real numbers. So f of n, the real number f on n, imagine that to be an estimate of the cost of the algorithm on inputs of size n. And let's suppose this is a recursive algorithm. So in order to process input of size n, the algorithm makes a recursive call, makes several recursive calls to itself with inputs with smaller inputs of size less than n. More specifically, let's just suppose the algorithm makes a recursive calls to itself each time with input of size n divided by b, so smaller, significantly smaller size. And what is a? A is some constant in the hypothesis, and b is another constant here. And also for realistic general analysis of algorithm, the recursive algorithm will probably need some time maybe to partition or otherwise subdivide or process the input of size n into these inputs for the recursive calls, each of size n divided by b. And this is to be covered with this big O of n to the d, where d is again another constant. And at the end of the recursive calls, the algorithm will need to perhaps recombine all the results from the recursive calls to produce the result, its own result. And this is also to be covered by this expression O of n to the d. So the basic message here is this kind of recurrences describe and analyze a large class of recursive algorithms that may take up to n to the d operations for splitting the original problem into subproblems, then making a recursive calls with subproblems of size n to the b, and then recombining the results of these recursive calls into original problem. You again incur at most cost t to the d. That's a hypothesis. And we have such a recursive algorithm where a, b, and d are supposed to be integers. Then the asymptotic cost of this algorithm described, or the asymptotic growth of the function satisfying this recurrence, is at most n to the d if a is less than b to the d, is n to the logarithm of a with base b if a is greater than b to the d. And in the intermediate cases, a is equal to b to the d, then the asymptotic growth is n to the d times log n. So these are the mathematical statements. And next, we're going to apply this asymptotic analysis to specific recursive algorithms for polynomial multiplication. So let me remind you of polynomial multiplication, the specification, and our agreeing on which operations we're going to use and how to analyze them. And then we're going to leave it at that for today. So polynomial multiplication specification is the following. The input consists of two polynomials. So here we have two polynomials, univariate polynomials, polynomial in one variable denoted x, and both polynomials are supposed to have degree less than n. Put differently, capital N is supposed to be large enough to cover all the degree of both polynomials. And having degree less than n, or put differently, having degree up to n minus 1 means that the first polynomial can be described using n coefficients, a0 up to an minus 1, and the same for the second polynomial, b0 up to bn minus 1, because we have only univariate polynomials. And the specification, the problem is to calculate the product polynomial, more specifically to return the coefficients of the product polynomial. Now, since the original polynomials have degree up to n minus 1, then the product polynomial has degree up to 2 times n minus 2. Therefore, the number of coefficients of the resulting polynomial is up to 2 times n minus 1, right? So counting also the zeros coefficient, 2 times n minus 1. So that's our problem specification. And next, we need to agree on which operational primitives to use and what costs to charge to them. And here we're going to simply count the number of arithmetic operations applied to the input coefficients. So input is 2 coefficient sequence of length n each, and output is 1 coefficient sequence of length 2 to the n minus 1. And we're going to simply count how many multiplications of AI by BJs are performed and how many additions and subtractions are performed. And what we're going to ignore is what kind of objects the AIs are, the coefficients, and we're going to ignore what kind of objects the B's are and what is their magnitude. So we're not going to do a bit-cut analysis for now. Later, of course, if we're multiplying integer polynomials, then it really matters what is the bit cost of the polynomials under consideration. If we multiply polynomials whose coefficients are matrices, then the size of the matrix matters and should be taken into account in the analysis and so on. So this is a specification for the polynomial multiplication problem. And next time we're going to look at a sequence of algorithms starting with long multiplication, then Karatsuba multiplication, then 2 multiplication, and then an infinite family of multiplication algorithms invented by Stephen Cook. And we're going to analyze these algorithms. They're all recursive algorithms using the master theorem that we discussed briefly. And then see that each algorithm is asymptotically more efficient than the previous one. So there's we're not going to arrive at the optimal algorithm at all here in this lecture. There is of course, the fast Fourier transform, but that's an entirely different type of algorithm and beyond the realm of this introduction to algorithm. So to summarize, today we've seen example of the meta loop and the paradigms of computer science and its virtues, namely Fibonacci number with 4 or 5 algorithms of increasing efficiency of smaller and smaller asymptotic cost. And we've analyzed these algorithms, and the algorithms use more and more powerful operations and fewer of these asymptotically. And some of these operations could and have been expressed in the bit cost to give a most realistic estimate and prediction of the performance. And these algorithms all make heavily use of the abstraction hierarchy, looking at the problem from a high level, using mathematical insights such as the matrix powering expression for Fibonacci numbers or the Binet's formula in order to arrive at algorithms that in turn use other algorithms such as the abstract powering algorithm, which in turn use other algorithms such as the recurrent algorithm for integer multiplications and algorithms for integer addition, which in turn are all based on bit operations. So abstraction, the power and the virtues of computer science illustrated at the example of Fibonacci numbers. Then we've closed with a master theorem of recurrences, analyzing the cost of recursive algorithms and their solutions, asymptotic growth. And next time we're going to continue and recall and continue with a polynomial multiplication problem. We're going to investigate and analyze the sequence of algorithms for that. That's all for now. Thank you very much for your attention and see you next time.